All right, hello, biology students. Today is April 30th. Yesterday in class, you spent some time practicing reading graphs. Today in class, we're going to ask you to use those same skills to look at some graphs with data about COVID-19. So this is going to be some pretty intense, pretty cool stuff. One thing I want to emphasize is you only have to choose one graph to study. So we're going to go over a handful of graphs. You do not have to watch this whole video. You should pick the graph you want to focus on and get ready to answer two questions. What could be a title for your graph? And what is a conclusion supported by the graph you chose? Again, kids, this video might be a little long. You don't have to watch the whole thing. Instead, you should just focus on one graph. So with that said, let's get this show on the road. I am going to begin explaining each of the graphs in today's class. Here we are. Skills practice, graph reading, COVID-19. Bang. All right. So, get my laser pointer ready. What up, laser pointer? Bam. All right, here is our first graph. So, we talk about independent and dependent variables just so we can kind of understand the relationship, what's going on here. So we see on this x-axis, we see date. Here are dates. And then we see on the y-axis, resource count. So we know that resource count depends on date. On different days, there are going to be more or less resources in use. All right, so here we have all beds needed. So that is all hospital beds needed. All hospital beds needed. Now, March 1st, we don't, it's going to be 0 hospital beds are needed for COVID. On April 1st, it's going to be something like, 100,000 hospital beds are needed for COVID. And you guys can read through what the rest of that is. All right, so ICU beds needed. Projected ICU means intensive care unit. So this is people who are really sick and how many intensive care unit beds are going to be needed. That's the green line. And again, you can see how the green line goes up and down over dates, noting that the resource is dependent on the date. All right, so now let's go to invasive ventilators needed. Now, you guys might have read about what invasive ventilators are. Those are essentially tubes that get shoved down your throat, pretty close to your lungs, and force you to breathe. And this is the blue line. How many invasive ventilators are needed? Now, I think the shaded area kind of stands for margin of error. So this is projected, but this is what it could be at the low end. This is what it could be at the high end. If we're to think about a title for this graph, I don't know, maybe it could be like resources available over time or resources needed over time for COVID. And, I'd wonder what conclusions you would draw from this chart. All right, kids, let's keep going. Okay, here's a really, really interesting chart. This one talks about, confirmed new cases, again, over time. I think you're going to see a lot of these COVID data charts. The dependent variable is going to be up here, and that'll change. But the independent variable is going to be over time. In other words, everything in COVID is going to be dependent on time. So here we are. We're looking now at like US confirmed new cases over time. In February, really not a ton. And we're following this light green line. And then look, here we are like March 15th, and see how it spikes and goes up and down. And then here's, April 26th. So it's a relatively recent data, and it's just floating around probably 40 something thousand people. And you can see, for example, like blue is Germany, light blue down here is Iran. You can see, China in green going up and down and then staying pretty low. So again, if we're looking at confirmed new cases, that's, we're sure that these are some new cases of COVID. Here is time. Each line has its own color, and each color represents a different country. And I'd be curious, what can, number one, what would you entitle this graph? Like maybe it's like countries confirmed cases over time, or different countries, different, number of cases, something catchy. And then what conclusion you'll draw. I wonder what conclusion this data will lead you to believe. All right, here is what is probably a very complex graph to read, but very, very interesting. So I'm going to walk you slowly through this one. All right, so let's start. What is going on the x-axis down here? You have event size. Notice 10, 100, 1,000, 10,000, 100,000 people. So here we have event size. And think of examples of what those events could be. The 10-person event is like a dinner party. The 100,000 person event is like a big music festival, like picture like Lollapalooza or something. All right. And then we have up here active circulating infections. All right. So if there are 10 people at a dinner party, and in a city or area or active circulating infections, or in US, there are only 10 active cases. I mean, this is saying like the odds of you getting COVID at this dinner party are somewhere between 6/1000ths of a percentage and 6/100ths of a percentage. That's crazy, crazy low. You can see that even if we get up to like 100,000 people, the odds of you getting COVID at a dinner party are still very low. All right, but if we get into 1,000,000 people who have COVID in the United States, there's about a 2% chance that you are going to get COVID if you attend a dinner party with 10 people. All right. So now here we have something like, a reception going on. We have a wedding reception where you have like 100 people. And you can see that if there are 2,000 cases, the odds of getting COVID are pretty low, about 6/100ths of a percent. But if there are a million cases, you got somewhere between a 2 or maybe even like 10% chance of getting COVID if you're at a 100-person wedding reception. All right, so I think to kind of elaborate what we are seeing here is, the odds that a person will get COVID if they attend an event. And we know that the independent variable here is how many people are at the event. The dependent variable is how many people, or no, sorry, one variable is how many people are sick. And then out here, you see the dependent variables. And this is how many, like, what are the chances that you're going to get sick if you attend an event? So, we've talked about low chances, but imagine there are 1,000,000 people in the United States who have COVID. Imagine you are at Lollapalooza and there are 100,000 people there. They're saying that there's about a 90% chance that you're going to get COVID. All right, so that is kind of the meat of this graph. Let's move on to the next one. All right, here's one that kind of gives you the title already. It is newly infected versus newly recovered. So, this is an important graph. I'm curious what kind of conclusions you'll draw looking at this graph. Here that the yellow line is going to be the newly infected. You see that this is time. Again, we're at April 26th when I got this data, and then new daily coronavirus cases or cured. So the yellow line is the cases, people infected. You can see how that changes over time. Green line are people cured. You can see that change over time. Boy, it'd be nice to see the number of people cured greater than the number of people, number of new cases. So I think an important conclusion is when the green line here is higher than the yellow line, it means something is going well. And right now, it's just it makes sense. It's not going absolutely terribly, but it's still very, very serious. It's something we can look at this portion of the graph to deduce. Of course, I'm curious what kind of conclusions you'll get looking at this graph if you choose this graph. I know these are two graphs, but it's the same kind of graph. This is probably the most technical. So if you choose this graph, props to you. So let's read it. It says US. The new cases confirmed each day's 5-day average. So here data is collected every 5 days and averaged the number of cases confirmed. And we're comparing the United States to Italy here. So it says the first case of COVID-19 in the US was reported 94 days ago on January 22nd, 2020. Since then, the country has reported 965,785 cases and 54,000 plus deaths. So the 5-day moving average of how many new cases is going up and then going up and down and up and down and up and down. If we were to call this a trend line, I know it's up and down, but it's still pretty much the same. In Italy, it says the first case of COVID-19 was reported 86 days ago on January 30th. Since then, the country has reported 197,000 cases, 675, and 26,000 deaths. And you can see how their average goes up, 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 and then slowly, even though it's going up and down, generally starts to decline. Okay. So I'm wondering what conclusions you might draw thinking about all the information presented on this graph. All right, so this last graph isn't a graph, it's something that we call an infographic, and maybe you'll choose to give a title to this and same way offer a conclusion. Pretty interesting information. Now this one talks about the average number of people that one person with a virus infects based on the RO scale. So the RO scale really is something that does just what this said. The RO scale is the average number of people that one person with a virus infects. So I mean, it's asking like if you get sick, how many people are you going to infect? Well, if you get sick with COVID, it's saying, there's on average, you're going to infect 2 to 2.5 people. If you had Ebola, which is another like terribly infectious disease, you'll infect between 1.6 and 2 people. If you have MERS, that was another virus that came out a couple years ago. MERS, you'll infect between 2.5 and 7.2 people. If it's SARS, another virus, you'd infect between 2 and 4 people. H1N1 was is flu virus. You'd infect between 1.2 and 1.6 people. So as you study this infographic, remember, think, what conclusions can I draw? Don't give me a detail. Give me a conclusion. What is true about the comparison between COVID and H1N1, or the comparison between COVID and Ebola, or what thought does looking at this make you have? All right, students, so that is all of the graphs. Good luck studying them. I cannot wait to see what kind of conclusions that you draw based on data. And remember, you only have to look at one graph. Kids, you rock. Miss you. Good luck with this. Reach out to Williams, Carr, Check, or me if you need help. Peace.